Welcome back to the deep dive. Today, we are cracking open the hood of what might be the most transformative piece of technology being developed right now, the AI agent.
Right.
And we're moving far beyond, the simple idea of a chatbot that just answers a quick question.
Carvia.
Our mission today is to really understand the core technological foundation, the entire stack that gives these agents their ability to, well, to perceive the world, to reason about problems, remember things, and I think most importantly, to actually take action.
And that holistic view is so essential. I mean, for anyone looking to really get this space, and this is critical, for you to actually design and build good agents, just listing the components is not enough.
Right.
You have to grasp how they all integrate. Thinking of an agent as just, an LLM with a few extra steps,
Yeah.
you're missing the entire revolutionary part.
So it's the system, not just the brain.
It is the system. We have to look at how natural language processing, NLP, the large language models, LLMs, retrieval augmented generation, or RA, function calling, how it all stacks up. The brain, the memory, the action layer, the sense, understanding that integration is the real shortcut to designing agents that are reliable, intelligent, and actually useful.
Okay, so let's unpack this with a clear roadmap. We're going to start with the agent's brain, the language and reasoning part.
Makes sense.
Then we'll move into that vital area of memory and context, which, is where RAG really becomes the star of the show.
Absolutely.
After that, we'll hit the real-world impact, the action layer, the plumbing that lets the agent actually do things. And finally, we'll explore the agent's senses, how it can see and hear using multimodal inputs. This is the whole toolkit, and we're going to dive deep into the technical why behind each piece.
Let's do it.
All right, let's start at the absolute beginning, the linguistic layer. Before we even get to these giant, complex LLMs that get all the headlines, we really have to talk about natural language processing, NLP. This is the fundamental ability that makes any of this communication with the machine even possible.
It's the bedrock.
Yeah.
100%. The core function of NLP is just enabling machines to understand, interpret, and then generate human language. Without that, the agent is, for all intents and purposes, mute and deaf to our instructions.
It doesn't matter how powerful the hardware is.
Doesn't matter at all. It's the linguistic parser that turns our raw text into concepts the machine can actually process.
And the source material we looked at details some really crucial practical abilities that make this foundational NLP so essential, even before the big LLM layer kicks in. Things like text classification and summarization.
And those are not trivial tasks at all. They are fundamental building blocks for doing anything at scale. I mean, think about an agent tasked with, say, legal compliance for a massive company. It doesn't have the time or the compute budget to read every single incoming document word for word right away. It needs that core NLP for text classification to determine instantly if a document is an internal memo, a vendor contract, a patent filing, or maybe just spam.
So it's triaging the information flow.
Exactly. That triage determines the agent's entire workflow from that point on.
It's about rapidly organizing and just filtering out all the noise.
Precisely. And summarization at this base NLP level is about condensing hundreds of pages down to the key actionable points or just the metadata. It enables much faster decision-making down the line. We're not talking about creative synthesis yet, just highly efficient data extraction and condensation.
Right. And then you have translation, question answering, and logical reasoning, all core NLP abilities.
Right.
How do these translate into specific value for, the learner looking at potential agent applications?
Well, these abilities are what power those high-value, really specific use cases we see across professional fields. For instance, generating a complex legal brief. That requires both accurate summarization and logical reasoning to synthesize arguments and, identify contradictions in existing case law.
Okay, that makes sense.
Or summarizing medical documents for a doctor. That needs highly accurate entity recognition and classification to pull out diagnoses and treatments. And maybe one of the most accessible examples, powering a chat-based tutor.
Right.
The agent has to constantly translate complex scientific concepts into simpler terms, adjusting its tone and vocabulary based on the student's level of understanding, all while managing follow-up questions in real time. NLP is what ensures the machine speaks our language clearly, logically, and with context.
And this is where the sophistication level just jumps dramatically. Once NLP lays that foundation, the capabilities are just amplified by large language models, LLMs. These are basically NLP on steroids, trained on these massive internet-scale data sets.
LLMs take those foundational NLP abilities, and they don't just elevate them, they completely transform them. We move past simple classification into these complex emergent capabilities. This is what allows the agent to synthesize rather than just summarize.
So it's creating something new from the information.
Exactly. We're talking about things like generating complex code, and not just little snippets, but functioning application logic. Creative writing that actually flows naturally. And the critical ability to manage multilingual inputs and outputs flawlessly across dozens of languages.
The interpretation of instructions is huge there, isn't it? I mean, an LLM isn't just following a command like a piece of old software. It's interpreting the user's intent. It's handling ambiguity.
Yes.
And it's formulating a complex, multi-step plan based on that interpretation, often across a bunch of different tools.
That ability to interpret complex intent and maintain intricate context over really long interactions, that is the hallmark of a modern LLM. This is where the magic happens. And when we look at the cutting edge, the source material names some highly sophisticated models. You've got GPT-4o, Claude 3 Opus, Gemini 1.5, Mistral, Llama 3, 5.3.
Yes.
These are the engines that provide that raw intelligence and complex reasoning. They're trained to predict the next token with such accuracy that the output just feels genuinely intelligent, coherent. It makes them the ultimate orchestrator in the agent stack.
But I want to linger here for a moment because the landscape it's not uniform. We have these giant commercial models, the proprietary ones, but the source material also highlights the importance of local and self-hosted options.
A very important point.
So for the learner, what is the critical distinction between, say, using GPT-4o through an API versus hosting Llama 3 locally on your own machine? What are the trade-offs there in cost, privacy, and performance?
That is probably one of the most important trade-offs in agent design right now. The proprietary models, like a GPT-4o or a Claude Opus, they offer peak performance. They often have bigger context windows, superior reasoning capabilities, and sometimes even built-in multimodal features. But they come with recurring inference costs for every single API call. And you are sending your data to a third party, which raises immediate data privacy concerns for any sensitive enterprise application.
So the open source self-hosted option solves those two big problems.
Exactly. Tools like Llama, LM Studio, and GPT-4o are really democratizing access. By running models like Llama 3 or Mistral locally or on your own private cloud infrastructure, you gain complete data security. No data ever leaves your environment.
Which is huge for certain industries.
It's critical. And crucially, while you pay for the initial hardware, the long-term inference costs just plummet, which makes them ideal for high-volume repetitive tasks. The trade-off is usually slightly lower peak performance compared to the absolute frontier models, and of course you have to manage the infrastructure yourself.
So if I'm building a specialized agent for a law firm, for example, handling extremely confidential client data, the ability to self-host Llama 3 becomes a critical security feature, and that might outweigh the minor performance edge of a proprietary model.
Absolutely. The decision about which brain to use dictates the security profile, the cost model, and the whole deployment strategy. Self-hosted models are critical for enterprises that need customizable, fine-tuned performance and guaranteed data sovereignty. It really underscores that the technology is becoming modular. It allows builders to choose the right brain for their specific agent based on security and budget, not just raw power.
Okay, so we have the brain. It handles the immediate thinking, the language generation, the instruction interpretation. But we all know that even the most powerful LLMs have this fatal flaw. Their internal knowledge is stuck in time. It's fixed at their training cutoff date.
Right, they're frozen.
They can't know what happened yesterday or access my company's private documents. So how does an agent solve this problem of memory, context, and external up-to-date knowledge?
Well, that leads us directly to the agent's memory system, which is where we address those very limitations of the LLM's fixed knowledge base.
So this is section 2.
This is where we get into context, recall, and grounding. If the LLM is the conscious thought process, then the memory layer provides the persistent context and the external knowledge that's required for any real-world relevance and accuracy. And this all starts with a concept that sounds a bit abstract, but it's foundational: embeddings and vector memory.
Okay, let's unpack this idea of embeddings. It converts data, text, images, audio into these numerical vectors. For our listener, why is converting language into a long string of numbers, sometimes hundreds of dimensions long, why is that so revolutionary for an AI agent?
It's revolutionary because it allows the machine to grasp the semantic meaning of data. It moves so far beyond just keyword matching.
Okay.
Imagine a massive conceptual library. A traditional keyword search, like in a SQL database, is like searching the index for the exact title of a book. If you look for fast vehicles, You only find things titled fast vehicles.
Right, very literal. But the vector system is different.
Totally different. An embedding process converts your legal documents or your emails or your company reports into these high-dimensional numerical representations. Data points that share similar concepts, even if they use entirely different words. Say, documents discussing subway systems, mass transportation, and rail commuter service.
All different words, same idea.
Exactly. They get numerically positioned close together in this conceptual space. So if your agent searches for rapid transit, the system finds the documents nearby that talk about subways and commuter rail, because the vectors capture that semantic equivalence.
So it captures conceptual proximity. That makes it incredibly powerful for nuanced search and for building long-term context.
Absolutely. And this is why embeddings are so crucial for document retrieval, for building a personal memory for an agent over long conversations, where the agent has to recall the gist of a prior discussion, not just the exact words, and for matching similar ideas across vast, disparate data sets.
And managing these huge arrays of numbers efficiently must require specialized tools and infrastructure. We're definitely not talking about a traditional relational database here.
Correct. When you're dealing with vectors of, say, 768 or even 1536 dimensions, the math of finding the closest neighbor becomes computationally really intensive at scale.
So you need something purpose-built.
You need vector databases. They're designed specifically to handle these high-dimensional arrays efficiently. The source list tools like FAIS, Chroma, Milvus, Weaviate, these systems are optimized for specialized challenges like index construction, and they use techniques like approximate nearest neighbor search, ANN search, to calculate that vector similarity really rapidly and at scale.
Yeah.
It ensures the agent can find the needle in the conceptual haystack almost instantly.
Okay, so this mechanism embedding's feeding into specialized vector databases. That then leads us to the superstar of agent reliability, retrieval-augmented generation.
Yep.
This seems to be the cornerstone of providing accurate, evidence-based outputs, especially in professional contexts.
RAG is arguably the single most important architectural pattern for reliable AI agents today. The core concept addresses that LLM knowledge limitation head-on. You store massive amounts of external data, your PDFs, internal policies, legal cases, long-term user instructions. You put it all in your vector knowledge base.
The library.
The library. When the agent gets a query, it first goes to its memory. It retrieves only the most relevant chunks of data from that knowledge base, and then, this is the key, uses the LLM to generate an output based only on that retrieved, verified external information.
I get the mechanism, but let's press on the why here. Why bother with this complex retrieval process when I could just try to, fine-tune the LLM with all my data?
That is the critical distinction. Fine-tuning attempts to bake the knowledge into the model's weights, which is expensive, it's time-consuming, and it still doesn't guarantee factual accuracy. Our RAG, on the other hand, offers three massive value propositions: higher accuracy, significantly fewer hallucinations, and maybe, most importantly, auditability and compliance.
Auditability. Explain what you mean by that in relation to our RAG.
Okay, so if a standard LLM answers a niche question, it might just confidently invent an answer. We've all seen this. A RAG-enabled agent, though, when asked the same question, is trained to retrieve the relevant document section, the evidence, and then generate an answer that is grounded in that verified text.
So it can cite its sources.
Often, yes. The agent can point back to the specific document and page number it used to form the answer. And that ability to trace the output back to a verifiable source transforms the agent from just a creative tool into a reliable, compliant research assistant. It makes it suitable for high-stakes applications like legal, medical, or financial reporting.
That breakdown makes it so clear that RAG is a sophisticated process, and it's designed specifically to enforce reliability. And the R pipeline isn't just one step, is it? It's a detailed sequence of operations that all have to work perfectly.
That's right.
Let's break down the technical steps involved here, maybe starting with the data preparation.
Okay. First, you have chunking. You can't just feed a 500-page book or a complex PDF directly into an LLM's context window. It's just too inefficient and expensive. So the data gets broken down into relevant, manageable chunks.
And the technique you use to chunk is important, I assume.
It's crucial. Simple fixed-size chunking, like 500 words per chunk, might split a critical legal argument right in the middle of a sentence.
So you need more advanced chunking techniques.
Yes. More advanced methods like semantic chunking or recursive chunking analyze the content structure, making sure that paragraphs or related sections are kept together. It preserves the conceptual integrity.
Okay, so after chunking.
Second, Those chunks are processed into embeddings, converting the text into those semantic vectors we talked about. Third, those vectors are stored in the vector DB.
And then comes the retrieval step when the user actually asks a question.
Right. The user's query is also converted into a vector. The system then searches the vector DB to retrieve, let's say, the top 10 or 20 most similar chunks. But here's the crucial refinement step, re-ranking.
Re-ranking.
Yeah, because raw vector search, even if it's semantically rich, it often brings up noise or context that is similar but not truly relevant to the core of the question.
So what does the re-ranker do?
A secondary, smaller, highly optimized language model, or sometimes a specialized algorithm, evaluates those 20 retrieved chunks against the original user query. It scores them for contextual relevance, and it prioritizes the 5 or 6 that are truly the most useful.
Ah, so it's a quality control step.
It's a critical quality control step. It ensures that the final LLM synthesis isn't confused by extraneous information. And finally, you have grounded generation, where the LLM synthesizes the final answer using only the prioritized relevant chunks provided to it. That maximizes accuracy and minimizes invention.
That entire sequence really showcases a system that's optimized for evidence and accuracy. And we see the applications for this everywhere now, connecting that generalized LLM intelligence to specific proprietary knowledge.
Absolutely. Think about agents in specialized environments. Legal research agents that have to recall specific, obscure precedents. Educational agents that need to cross-reference historical facts against specific textbook definitions. Business intelligence agents use RA to analyze internal sales reports and market data that their LLM brain has never, ever seen.
So RA is the bridge.
RA is what connects the generalized knowledge of the LLM to the specific proprietary and current world of the user. And that's what makes it reliable enough to operate in virtually any field.
Okay, so the agent can think, and it can remember and verify its information. But thinking and remembering are, at the end of the day, useless if it can't actually do anything in the real world.
Right.
Like sending an email, logging data, or executing a trade. And that brings us to the crucial action layer.
Now we're talking.
This is the definitive line between a sophisticated chatbot and a truly autonomous AI agent. The action layer allows the agent to move beyond generating text into interacting with external systems, executing tasks, and ultimately automating real-world workflows.
This is where the utility just explodes. The agent becomes an active participant in your workflow, not just a passive respondent. And the core enabling mechanism for all of this is function calling, or as it's sometimes called, tool use.
Okay, explain that bridge for us. How does the LLM, which works primarily with language, how does it decide to output executable code or a system command instead of just a natural language reply?
Well, function calling is the instruction set, or maybe more accurately, the predefined schema that allows the LLM to realize, okay, my next step needs to be an action, not a reply.
So it knows what tools are in its toolbox.
Exactly. When you prompt the agent, you provide it not just with your query, but also with a list of tools it has access to. For instance, send mail, recipient, subject, body, or query database, school query.
So the LLM receives the definition of the tools it can use.
Precisely. And based on the user's intent, the model predicts the most relevant next step. If you say, schedule a meeting with John for next Tuesday, the LLM doesn't say, I will schedule a meeting. Instead, it outputs a highly structured JSON payload that conforms to that function schema. Something like function name, schedule calendar event, arguments, user, John, date, next Tuesday, time, 2 p.m.
And then something has to catch that JSON and do something with it.
Exactly. That JSON payload is intercepted by the agent's operating system and used to trigger the external tool. In this case, the Google Calendar API, for instance.
That is the moment the agent's intelligence turns into real utility. What capabilities does this technical mechanism unlock in terms of real-world impact?
It allows the agent to interact with the entire world of enterprise software. I mean, we're talking about triggering external tools, operating complex multi-step workflows, and critically submitting data or querying live up-to-date databases. This isn't just internal memory recall with RAG. This is connecting to live external data streams and systems.
Okay, give us some concrete examples of agents using function calling to execute some of these complex tasks.
We see clear examples across so many domains. An agent tasked with personal finance could use function calling to submit tax data directly to an online portal using the appropriate API, securely transmitting structured data.
Okay.
Or consider the legal context again. An agent could pull specific up-to-the-minute case law data from a private proprietary database that is totally inaccessible to the LLM's general training data. It does that by generating a query via an SQL function call.
So it can interact with anything that has an API.
Anything. And furthermore, agents often use specific language functions, like Python functions, to generate files or documents. The agent isn't just telling you how to draft a contract. It's actually generating the document, formatting it correctly, and saving it as a PDF or a docx file ready for you to use.
So execution is key. But action also requires persistence and scheduling. I mean, an agent that only works while you are actively prompting it in a chat window is just a tool. To be a true agent, it needs some autonomy.
Exactly. And that autonomy comes from automation engines.
Right.
These tools handle the task scheduling, the recurring actions, and the asynchronous operations that give the agent a persistent presence in a workflow. It decouples the agent's work from the user's immediate attention.
So it can work in the background.
It has to be able to work in the background. An agent needs to be able to say, I need to run this report every Friday at 3 p.m., whether the user's logged in or not, and then report back to them via email.
And we're seeing a whole ecosystem of dedicated, reliable tools for this. Zapier, Make, which used to be Integromat, AAMen, custom OpenAI automations. What role do they play in the agent's overall infrastructure?
These tools act as the operational backbone and the timekeeper for the agent. They allow the agent to exist within established business and personal workflows by providing these reliable triggers and connectors. They manage state across multiple applications.
Can you give an example of that?
Sure. Take the example of a weekly legal brief summary workflow. The agent uses function calling to search a database for new cases. It uses the LLM to summarize them, and then the automation engine, like Zapier, kicks in to ensure that summarized brief is emailed to the entire legal team every Monday morning without any human intervention.
Or even just managing recurring personal tasks.
Absolutely. Think about complex financial management, a monthly rent calculation that needs to pull data from a bank API via function calling, compare it to a lease agreement that's stored in our knowledge base, and then trigger a payment through a payment portal all on a fixed date. The source also mentions specialized examples like creating a daily Quran study plan, which shows the application in these deeply personal and niche organizational tasks.
So the automation engine is what turns the intelligent tool into a persistent, autonomous employee that works on your schedule.
That's a great way to put it.
Okay, so we have the brain, the memory, and the action layer. But all of this so far has relied on us providing clean, structured text input or the agent generating text output. What happens when the world doesn't provide nice, clean text? What about images, video, and audio?
That's where the agent senses come in.
Yeah.
And for that, we need multimodal perception to process the chaos of the real world.
All right, let's get into the senses.
We have to realize that modern AI agents are just no longer text-locked. They have to interact with a world that is full of visual, auditory, and structural data. So multimodal capability means the agent can understand and process all these diverse input types: images, raw audio streams, video files, screenshots of software, even complex PDF pages with diagrams and tables.
But the LLM, the brain, it still works primarily with tokens and language, right? So how does an agent take a raw image of a diagram or a 30-minute meeting recording and turn that into something the LLM can actually reason about and use to inform an action?
That requires significant preprocessing. The raw, unstructured, non-textual data needs to be converted into a usable format, which is typically text or some kind of structured vector representation that the LLM or a specialized model can handle.
So it's another layer of tools.
It's a whole suite of specialized, often traditional computer vision and speech tools working before the LLM even sees the input.
Okay, so which pre-processing tools are essential here?
Well, for reading documents, even challenging handwritten or scanned ones, you need robust OCR optical character recognition tools. Things like Tesseract or Paddle OCR. These are critical for agents that have to handle archival paperwork, legal discovery, or historical data.
And for audio?
For audio inputs, like recorded meetings or phone calls, you need state-of-the-art SCT speech-to-text engines. Whisper is the most famous one. They transcribe the audio accurately into text, which can then be summarized or analyzed by the LLM.
What about for visual media, like video?
When you're dealing with video or complex images, tools like FFmpeg are used to extract specific video frames at intervals. That essentially turns a video into a sequence of images. Then, a tool like OpenCV can perform initial image manipulation, like cropping or feature extraction. These pre-processing steps ensure the agent can effectively read documents, understand photo content, and summarize video. It gives the agent true sight and hearing before the intelligence layer even kicks in.
And once that visual data is pre-processed, it then feeds into dedicated vision models. And this is where the agent moves far beyond just, labeling a photo as dog or car.
Exactly. Vision models are tasked with extracting structured, high-level information from visual inputs, be it images, complex diagrams, or real-world scenes captured via a CCTV camera. Their core capabilities include object detection, where they locate and identify items.
Like a self-driving car does.
Right. And scene understanding, where they grasp the context of what's happening. For example, a person is operating a machine in a factory. And what's critical for business documents, layout analysis, so understanding where titles, paragraphs, tables, and figures are placed on a page. That's vital for extracting structured data from unstructured visual media.
I was really struck by a specific intriguing detail mentioned in the source material: facial occlusion detection. Why is that specific high-level capability so critical for agents?
Facial occlusion detection is important because it's a very detailed visual analysis that allows the model to not only detect a face, but also verify if it's fully visible or if it's obscured by, say, a hand, a mask, or a shadow.
Okay, I see.
In security or privacy-focused agents, this ability allows the system to verify compliance. Is the subject wearing required safety gear? Or conversely, it can ensure that data is properly anonymized before it gets processed. It really shows the granularity of information these models can now extract.
And where are these vision models actually being applied in the real world?
They're everywhere. Visual data is key. Legal document camera agents use vision models to scan, verify, and organize complex briefs instantly. Website UI testing agents use vision to confirm that buttons and elements are correctly displayed on a screen, checking against known good layouts. Product image analysis agents can check quality control on a manufacturing line for defects. And of course, CCTV and anomaly detection agents are constantly monitoring feeds for unusual activity, relying entirely on advanced scene understanding.
Let's talk a little more about the specific technologies that handle sound and motion, so speech and video technologies. We need to differentiate between the agent speaking and the agent listening.
Right, there are two core speech functions we need. Speech-to-text, or SDT, using models like Whisper or Vosk, converts human speech into text. That's essential for transcribing meetings, handling voice commands, or analyzing customer service calls.
And the other direction.
Conversely, you have text-to-speech, or TTS, using tools like Piper, Koki TTS, or Azure TTS. That converts the agent's generated text back into high-quality, natural-sounding voice instructions.
And this combination is what lets you build truly interactive, voice-based assistants, or enables things like the automatic creation of spoken content, like a podcast.
It creates that two-way street of auditory interaction. It allows the agent to have a truly natural voice interface.
What about video?
For video, the complexity just ramps up significantly because the data is sequential. It's not a static image. Video understanding models have to extract meaning from sequences of visual and auditory data over time. Core features here include scene segmentation, so breaking the video into meaningful thematic sections, captioning, motion tracking to follow specific objects or people across frames, and what's critical for content creators, audio-video alignment to ensure everything is synchronized.
So an agent can essentially watch a video and understand the narrative arc and the flow of information, not just what's in a single static frame.
That's the key breakthrough. And this is used extensively in security agents for complex threat detection over a timeline, lecture-to-summary agents that process hours of educational content into concise, chronologically structured notes, and sophisticated video editors or social content agents that can automatically clip, caption, and edit footage based on high-level textual instructions.
So you could just tell it, create a 10-second highlight reel of all the moments the speaker mentions RB.
And it would do it. The multimodal stack gives the agent eyes and ears to navigate our digital and physical world effectively.
We've covered thinking, memory, action, and perception. But all of this, whether it's the 600-word Python script, the 5,000-dimensional vector, or the 3 terabytes of user data, it all needs a home.
It does.
What are the physical and virtual systems required to store and deliver the agent? We need to talk about infrastructure.
Absolutely. The greatest AI brain in the world, equipped with perfect memory and senses, is totally useless if it can't maintain state, manage massive data volume, and isn't reliably accessible. Infrastructure provides the necessary physical and virtual systems to sustain the agent's operation 24/7.
Okay, so let's start with databases and storage systems. We already touched on vector databases for our guy, but what distinguishes these more general storage systems? What are they for?
These systems manage everything else. They store the long-term non-semantic memory, the user projects, the application data, and the files. So while a vector DB stores the meaning of the data for retrieval, traditional databases store the structure of the agent's operation. They're crucial for maintaining state and continuity.
And what are the common tools we see agents relying on for this kind of persistent storage?
We see a pretty sophisticated mix, really based on the agent's needs.
Ah,
We might see relational databases like Swite for simpler, localized storage, or maybe PostgreSQL for more complex transaction management. We also see a lot of non-relational real-time backends like Firebase and Supabase, which are often used in web applications for dynamic data updates.
right.
Notion Database is increasingly being used for flexible, document-centric storage of project outlines and logs. And for all those vast multimedia files generated by the multimodal snack, cloud storage like Google Drive or OneDrive is pretty much essential.
And what specific agent data are they keeping in these databases? What's the most important stuff?
Three things are crucial. First, they need a place to cache results to avoid redundant, expensive LLM calls. If an LLM answers a complex query, the result is stored so the agent can instantly retrieve that answer if the query is repeated, saving both cost and time.
Makes sense.
Second, they store user profiles, which contain preferences, permissions, and historical interaction data vital for personalization. And third, and this is most critical for reliability, they keep progress logs. If an agent is performing a multi-step task that takes 3 hours and it gets interrupted, the database ensures the agent knows exactly which step it completed last. That ensures persistence and reliability.
Finally, we need to discuss deployment technologies. We have this incredible, complex, multi-component stack. How do we make it scalable, reliable, and available to the end user without requiring them to have a degree in cloud engineering?
Deployment is the delivery mechanism. An agent needs to be scalable, fast, and accessible wherever the user needs it to work. It needs to meet the user where they are, on dedicated websites, as chat plugins integrated into Slack or Teams, running as native phone apps, or even as browser extensions that interact with specific web pages.
So this means the actual technical deployment has to handle everything from hosting static front ends to managing complex serverless functions and these large computationally intensive models.
Precisely. We need modern deployment stacks that are capable of handling varying loads, complex dependencies, and ensuring reliability. The source names some crucial tools here. For instance, Docker provides containerization, which is just non-negotiable for complex AI stacks.
Why is that so important?
It packages all the agent's code and dependencies, the specific version of Python, the vector database client, the multimodal libraries, into a consistent, reproducible environment. This prevents those "it works on my machine" issues when you're trying to scale up.
Right. And what about speed and distribution?
That's where services like Vercel and Cloudflare Workers really shine. They're excellent for fast, serverless deployments. They're often used for the front-end interface and the API gateways that manage the quick input-output requests. Their use of edge computing ensures extremely low latency for users all over the world.
And for the back end.
Tools like Railway provide robust platforms for rapid development and scaling of the back-end services, while Hugging Face Bases is excellent for sharing models and demos quickly.
So the agent starts as code, it becomes intelligent via LLMs and RAG, it gains the ability to act via function calling, it perceives the world multimodally, and then finally it's served up scalably and reliably through these sophisticated deployment platforms. That really is the full integrated picture of an operational AI agent.
That's the full life cycle. Without robust infrastructure and reliable deployment, the agent just remains a fascinating prototype instead of a powerful, autonomous, and operational tool that's ready for high-stakes enterprise use.
What a complete picture this provides. We've really gone through the full technological anatomy of a modern AI agent. Let's just quickly summarize the integrated technology stack we've uncovered. We saw that NLP and LLMs provide the intelligence and complex reasoning, that's the agent's brain. And we now understand the crucial trade-off between proprietary and open source models.
Right.
We detailed how embeddings and RAG manage external knowledge, ensuring auditability and accuracy, that's the agent's memory.
The grounding.
Then, function calling and automation engines enable real-world execution and scheduling the action layer. And finally, multimodal processing gave the agent its sophisticated senses, allowing it to interpret images, video, and audio.
And the essential takeaway for you, the learner, is the integration. The LLM is merely the coordinator, but it is the external tool integrations facilitated by APIs and function calling that provide the genuine, active, action-taking capability. And it's the combination of advanced memory via array, paired with persistent infrastructure and automation engines that provides reliability and sustained operation. This modular integrated stack is what enables AI agents to be truly cross-domain autonomous workers.
And that integrated value means that agents can now tackle virtually any field, from law and medicine to specialized manufacturing and personal finance, because they can read the proprietary documents, remember the specific rules, execute the required tasks automatically, and then report the results through reliable infrastructure. It really moves AI from being an oracle to being a partner.
Which brings us to our final provocative thought for you, the listener. If this complete technology stack, the brain, the memory, the action, and the senses, is rapidly conquering professional domains, what is the next, more specialized domain that will be fundamentally reshaped by this technology? Consider hyper-specialized scientific research fields, deep personal development goals, or extremely niche hobbies. Where does this comprehensive stack create its most surprising, revolutionary impact next, and how would you build that agent?
That is definitely something to chew on. Understanding the components of the stack is really a first step toward building the future. Thank you for joining us for this deep dive into the core technologies behind AI agents. We hope this has given you the foundational knowledge you need to start building, designing, or simply understanding the next generation of intelligent software.
It's always a pleasure diving into the source material with you.
We'll catch you next time for the next deep dive.